discuss now a very nice example from Fox and McDonald. We will clearly understand the use of substantial derivative, and then the Eulerian frame of reference, Lagrangian frame of reference, etc. Okay. Let me read the example. Consider two dimensional steady incompressible flow. Two dimensional because you have velocity variation in the x direction and in the y direction as well. Steady, as we have seen earlier, at a particular point there is no change in velocity. Incompressible flow we will discuss later. As of now you can just say it is a something like a constant density flow. To the plane converging channel. Why is it plane? The configuration is such that you have two planes like this. Usually a nozzle has a cylindrical geometry, okay, but that will take us to cylindrical coordinate system. But we want to, there again of course there is increase in velocity, acceleration takes place, but to make life simple and consider a simple geometry, we are considering two planes like this converging to each other. That is why it says plane converging channel shown. The velocity on the horizontal central line, is given by this velocity field. So far we have been telling velocity field, the first time coming across a expression for a velocity field. Okay. Now we know that this v vector has three components, vx, vy and then vz. In this particular case we have only the x component because the vector here is I vector. So either you can say Vx is equal to this or say V vector is equal to this expression along with the I vector, two ways of giving you the velocity field. Now why does it say on the horizontal central line? The reason is that if you are away from here there is a y component also. So only along this central line there is only x component of velocity. Once again to start with a simple example, we are considering along the central line. If not along the central line, I should consider both Vx and Vy. Once again, so this that is why the example is so well simplified, but at the same time gives you all the concepts. That is a good example, that is a definition of a good example. Okay. What is that it asks to find out? Find expression for the acceleration of a fluid particle, moving along the central line. What is that? We have a particle here and it moves along the central line. What is the rate of change of velocity as experienced by the fluid particle? Okay. And then we are asked to evaluate the acceleration when the fluid particle is at the beginning and at the end of the channel. We will use two approaches to solve for the acceleration of the fluid particle. First is the Eulerian approach and then using the Lagrangian approach. Okay. We will clearly see what is the difference between these two approaches, what is the independent variable, etc. The dependent variable is of course acceleration. Okay. Now substantial derivative of velocity gives acceleration of fluid particle in terms of Eulerian field variables. We have seen that, we are going to illustrate that in this example. Substantial derivative of velocity which is from the Lagrangian viewpoint, that gives the acceleration of fluid particle. We are asked to find out this in terms of Eulerian field variables. We said to find acceleration we require velocity field and that is what is given to us. We are going to use the velocity field to get the acceleration of fluid particle. Okay. So what I have written here is the acceleration in the x direction of the particle, either you can write as APX or AXV. Okay. AX represents acceleration x direction of the particle as a function of x, y, z and t. These are all Eulerian spatial locations which are very familiar every time. Okay. Okay. And of course represented as dvx by dt, you have the local component, you have the convective component. In this case it is a steady state. So this component will not play a role, we will have only the convective component. Even in the convective component because we are along the axis, there is no y component of velocity. Of course, we are considering only 2 dimensional case. So, there is no z component of velocity, this is something perpendicular to the plane of the slide. Okay. So, there is no z component, and so since we are along the axis, there is no y component, otherwise you would have y component as well. Okay. All these are taken so that you get a very simple expression, so that you can understand and focus more on the physics and whatever concepts illustrated by the example. Okay. So, now our expression becomes simplified. A x p is equal to this dvx by dt. Of course, this is anyway 0, still I am retained, but these two terms v y is 0, v is at 0, you are left only with this component. Okay. And we are given the velocity field x component of velocity as a function of x. Okay. Let us see what does this mean, how does this velocity intuitively represent the flow. V 1 into 1 plus x by L, let us say x equal to 0, the velocity is V 1. What does that mean? The velocity in terms of Eulerian representation, the velocity at this particular location is V 1. Now, when you substitute, let us say if you take a channel of length L and substitute x equal to L here, this becomes 2, and the velocity here is twice of V 1. That is what, and this of course gives you the velocity at any x along the horizontal axis. That is the interpretation for this velocity field, and it is a steady flow as we have been discussing. And so, this term goes off, dvx by dt, first term is 0, and then you substitute for this velocity field Vx here, and then differentiate that with respect to x, partially with respect to x. In this particular case, you can write as dvx by dx, because there is no y variation, z variation, time is also not there, but generally we write as dou vx by dou x. So, this represents Vx, and then this represents dou Vx by dou x, and when you simplify you get this expression V 1 squared by L 1 plus x by L. Now, acceleration of this particle is V 1 squared by L 1 to 1 plus x by L. How do I correctly tell this? Let us say if you want to tell in words, acceleration of any particle, okay, that is at a point x at an instant, at a particular instant you have a particle here, and what is its acceleration? So, acceleration of any particle. Okay. Remember, we said substantial derivative relates Lagrangian representation in terms of Eulerian location, that is what exactly is shown here. Acceleration of any fluid particle, that is at a point x, x is something like our spatial location, at an instant is given by this expression. So, if you substitute x, different values of x, you will get the acceleration of fluid particle as a function of axial position. Okay. Okay. Particle experiences acceleration even though the flow is steady. What do you mean by steady flow? At a particular position there is no variation of velocity with respect to time. So, it is steady state flow, but because the velocity increases along the direction of the flow, the fluid particle experiences an acceleration along the direction of the flow. So, particle experiences acceleration even though the flow is steady. Usually we associate acceleration with some rate of change with respect to time, but in this case when we say acceleration, you travel along with the fluid particle, you experience a change in velocity as you travel, resulting in an acceleration. Okay. Now, as I told you, this gives the acceleration of particle as a function of a spatial location which is x coordinate. We want to find out, the question says find out the acceleration at the beginning, at the end, which means we have to just substitute x equal to 0, x equal to L, and that is what we will do now. So, when the particle is at the beginning of the channel, x equal to 0, so the acceleration is given by V 1 squared by L, and that is the acceleration at the beginning of the channel. Okay. Now, when the particle is at the end of the channel, x will be equal to L, and we get the expression for the acceleration of the particle at the end of the channel, which is twice the acceleration at the beginning of the channel. Okay. So, in this particular case, not alone the velocity increases along the channel, the acceleration also increases along the channel. Okay. So, V1 squared, so acceleration is also twice of that at the beginning of the channel. What we have done now, we have followed a Eulerian approach. Why Eulerian approach? We use the field information, velocity field information. We got a nice meaning for substance derivative. The whole thing is achieved because of the significance of substance derivative. Just substituted in that, got the acceleration of fluid particle. Now, what we will do is get the same expression following a Lagrangian approach. What is the why are we doing that? So that we understand what do we mean by Lagrangian approach, what do we mean by Eulerian approach. Okay. Now, in the Lagrangian approach, what is required is the position of the particle as it flows through the this converging nozzle. So, if you are experimentally measuring, then you will have the position as a function of time, but in this case, because in the example we do not have that information. So, what we will do, we will use the velocity field itself to get the position as a function of time. Okay. Let us do that. So, what we are going to do is arrive at the same expression at the beginning and end of the channel for the acceleration of fluid particle, but following a Lagrangian approach. Okay. Okay. So, obtain motion of fluid particle as in particle mechanics. Exactly what you do in particle mechanics for a single particle, we do that here for a fluid particle. Okay. To emphasize that, I put that as a first statement, obtain motion of a fluid particle as in particle mechanics. Remember, we said Lagrangian is a natural way because it all carries over from particle mechanics. Okay. We are going to use that approach. Now, because we said particle mechanics, we know that the velocity of the particle can be obtained by differentiating the position of the particle, simple differentiation d by dt. Then we can get the acceleration of the particle by differentiating the velocity of the particle. Okay. All these are exactly what you would have discussed in your physics class. For a solid particle, we are now extending to a fluid particle. Now, how to get the position of the particle? Okay. As I told you some time back, if it were experiments, we would follow the fluid particle, know its position as a function of time. Being an example, here we will use the Eulerian velocity field itself to get the position of the particle as a function of time. What do I mean by that? You start here t equal to 0, you specify some time, I want to know what is the position of the particle, what is the position of the particle given a particular time. Okay. Okay. How to get position of the particle is a question. Okay. Now, we have used this during the derivation of the expression for substantial derivative. We will use the same physical principle. At any instant of time, the velocity of the fluid particle is equal to the local value of velocity field at the location. Okay. This does not mean that the Eulerian velocity is equal to Lagrangian velocity. Okay. What it means is two ways of understanding this expression. You have a flow field, okay, and then you are at a particular location. The velocity at that particular location, the velocity at this particular location is equal to the velocity of the fluid particle which happens to be at that particular location, that particular instant. Okay. After all, fluid particle represents the flow. So, both velocities should be same. I will repeat again, you are at a particular location, the velocity of the fluid, which is the Eulerian description, should be equal to the velocity of the fluid particle which happens to be at that particular location, that particular instant. Looking, this is first I told the right hand side, then I told the left hand side. I will just repeat the statement, but in the reverse direction. Looking at the particle point of view, we are tracking the fluid particle, it is at a particular location, its velocity is same as the velocity of the fluid at that particular location. Here I have told the left hand side first and then the right hand side. I will repeat that, tracking a fluid particle and then it is at a particular location, at this location its velocity is equal to the velocity of the fluid, okay, the Lagrangian to Eulerian. Now, so velocity of the particle in the x direction is equal to the Eulerian velocity, but replacing x by xp, position of the particle. Okay. Now, we know that this velocity of the particle is nothing but the derivative of the position. So, I instead of this velocity of the particle, I replaced with the derivative of the position of the particle. Right hand side, we know that this is the Eulerian velocity, but now it is at a particular location where the particle is present. So, I replace here x by xp. So, same expression V 1 into 1 plus, instead of x I replace xp divided by L. What does this equation tell you? This will tell you what is the rate of change of the position of the particle in terms of x direction, how is it related to the Eulerian field replacing x with xp. So, we have got a differential equation for the position of the particle, dx by dt is in terms of the right hand side. Okay. That is where we will continue in the next slide. So, dxp by dt, rate of change of position of the particle, is equal to V 1 into 1 plus xp by L. So, it is a differential, first order differential equation. Xp is the dependent variable, time is independent variable. We need one initial condition for this. So, we will say at time t equal to 0, the particle is at the beginning of the channel. So, I integrate this equation, do a variable separation, bring this to the left hand side and dt to the right side. What are the limits? At time t equal to 0, the particle is at x equal to 0, in this case xp equal to 0, okay. And then at any time t, the particle is at any position xp. So, we are just the differential equation which are integrating given the condition, and doing simple variable separation, integrate this, okay. This becomes of course ln 1 plus xp by L and then another L there, this becomes V 1 into t. Our objective was to get the position of the particle as a function of time. So, rearrange this equation, so that you get expression for position of particle as a function of time. What does the time mean? As I told you, the particle starts here, you would start your time and then it travels along the channel and time starts ticking away, okay. And this gives you at any time instant where is the particle, here, 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 etc. Okay. Okay. Of course, now once you got the expression for the position of the particle, as I told you some time back, in this case we have got it from the velocity field. If it were an experiment, let us say we discuss a particle image velocimetry, you would get this in experimental data. Okay. Once you got the position of the particle, then the simple differentiation will give you velocity, one more differentiation will give you the acceleration, that is what exactly we are doing. The velocity, and that is why this is exactly same as particle mechanics applied for a fluid particle. Okay. Now, the velocity of the fluid particle is equal to the first derivative of the position. So, you get this velocity, and then acceleration of the particle is once again you differentiate the velocity, you will get the acceleration of the particle, differentiate with respect to time, and then you will get the acceleration of the particle. Okay. What is to be noted here is that the velocity, or in fact the position, velocity, acceleration are all functions of time. Remember, a Lagrangian description, what are the independent variables? Initial position vector, initial position and time. In this case initial, and then we said Lagrangian independent variables are for a particular fluid particle. What is a particle? Remember in our chimney example we said particle A, particle B, particle C. Two independent variables, one is initial position and then time. In this case, because we are focusing on one particular particle, that initial position does not appear, but indirectly it is there, it is for this particular particle, let us call particle A. Explicitly what is the independent variable that is appearing in the equation is the time. Two independent variables, but because we are focusing on one particle, let us say A, only one independent variable time eventually appears in the final expression. That is to be noted, that is a distinction between an Eulerian representation and a Lagrangian representation. Eulerian representation, the acceleration of the particle was in terms of x. If you specify x, I can calculate the acceleration of fluid particle. In this case, the acceleration of fluid particle is in terms of the time, because we are working in Lagrangian representation, okay, and that is what. So, acceleration at any time t of the particle, that was initially at x equal to 0. Okay. So, one independent variable is t, another independent variable is hidden here. Okay. We said particle A initial position, and that is what is specified here, and then another independent variable is time. acceleration of at any time t of the particle that was initially. So, which means you are fixing a particle. Okay. Now, the question said what is the acceleration of the particle at the beginning of the channel, at the end of the channel. It did not tell us time, there was no time straight away involved in it, but now because we follow Lagrangian approach our expression involves time. So, we will have to get the time position relationship. We know the position, we have to find out the time. Okay. Now, to find acceleration of particle when x equal to 0 and x equal to L in Lagrangian approach, as I told you now, acceleration of particle is expressed in terms of time. Okay. So, need to find out the time at which particle is at the beginning and the end. We are given the position, we need to find the time. Why do you need a time? Only then I can find out the acceleration of particle using the Lagrangian approach. How do we do that? We have got expression for the position as a function of time. Use the same expression, but now what I want to find out is this time, I know the position. From the velocity field we integrated it and got an expression for position as a function of time, but now I want to find out the time given the position. So, just rewrite it to find out the time, and we know that first is the position x p equal to 0 beginning of the channel. We have taken that as our initial condition t equal to 0. So, x p equal to L at the end of the channel, you substitute L here and find out t. So, if you do a simple algebra, you will find that t is given by this expression. What is it we have done in these 3 steps? We derived an expression relating the position as a function of time. Now, we know the position, we have to find out the time. First one x p equal to 0, and either by substitution or even by physics we said that the particle is here at time t equal to 0, which is x equal to 0, x p equal to 0 corresponds to time t equal to 0. Now, x p equal to L, the particle is here. So, substitute L here, do a simple algebra, you will get t as L by V 1 ln 2. What does it mean? The particle is at the end of the channel at the time given by t equal to L by V 1 ln 2. L is of course the length of the channel. Okay. Now, what is that we should do? To find out acceleration, we need to substitute this time there. We have got both the time at the beginning at the end of the channel. So, substitute t equal to 0. So, this becomes unity, that is the acceleration of the particle at the beginning of the channel, same as what you have got from the Eulerian approach. In the second case, the time is given by L by V 1 ln 2. So, substitute here for t, or you can also substitute e V 1 e power V 1 t by L is equal to, either way you can do it, and you will get the acceleration as twice which was at the beginning of the channel, same expression which we obtained from the Eulerian approach. So, very nice example which clearly illustrates the first the use of substantial derivative. You give me velocity field, I will give you acceleration of fluid particle using Eulerian variables alone. Second approach, we use a Lagrangian approach, we all worked in terms of Lagrangian position, velocity, acceleration, but now time is a variable. We found out what is the time corresponding to the position and then result. Okay. And that is what I will show here. I have taken a channel of length 1 meter, okay. I have taken the velocity as V 1 at the beginning of the channel as 0.1 meters per second. Okay. Let me run the first video. Now, this what has happened is the particle has started here, okay, and then it has moved through the channel till the end of the channel. I have done this simulation from t equal to 0 to t till it reaches the end of the channel, okay. And in this case it was roughly about 6.9 seconds, okay, 0 to 6.9 seconds. Now, these are position of the particle at equal time intervals of 0.69 seconds, and as you see the distance moved is increasing as it travels along the length of the channel. Each gives a position at interval of 0.69 seconds. For the same time duration, it covers a longer distance as it moves towards, as it goes through the channel, obviously because of higher velocity. The fluid experiences higher velocity as it goes through the channel. So, it travels longer distances for the same time interval. Now, let me show again here. Here I have shown the successive position of particle and the entire particle trajectory as well. Okay. Here I am just showing the instantaneous position of the particle. So, what I have shown here is, let me just stop for a moment and then continue. This shows what happens as the fluid particle flows through the channel. I have shown here the time. Okay. As I told you, I simulated this from 0 to 6.9 seconds. Roughly that is time where it reaches the end of the channel for these and it also shows the, remember we have got expressions for the position, the velocity and then the acceleration of the particle. So, I have shown the velocity, the position of the particle, the velocity of the particle and the acceleration of the particle, and as the particle moves through the channel they keep changing and you can take a look at it. So, you should focus, for example, this time increases by increments of 0.1 and accordingly the spatial location changes, this velocity will increase, the acceleration also increases. Remember from our expression the velocity also doubles, acceleration also doubles, and that is what happens here. The time increment is 0.1 second. The run simulation for every 0.1 second, the x coordinate and the velocity, and then so let me just, so I done simulation for 6.9 seconds. So, almost at the end of the channel 1 meter, and the velocity has increased from 0.1 meter per second to 0.2 meters per second. Acceleration increased from 0.01 meter per second squared to 0.02 meters per second squared. Okay. That is what happens. Whatever you have seen more mathematically in terms of expression is shown in terms of simulation. Okay. Fine. Okay. Okay, just to we have gone through a series of steps. I thought I will just summarize them here. The Eulerian approach, we were given the velocity field, we find acceleration of particle as a function of position using substantial derivative, okay, and find acceleration of particle at required position, because the expressions themselves are dependent on position. So, given the position just substitute, find out the expression, very simple. Lagrangian approach, Lagrangian approach, given the velocity field, but we are not using it directly, find the position of particle as a function of time by integration. That is the first step we did. Once you know the position, differentiation once, twice will give you velocity and acceleration of particle as a function of time, that is to be noted. Now, we need to find out time corresponding to the required position, that is what we did, because we know the position as a function of time. Then substituted in the expression for acceleration which was in terms of time. Okay. So, now look at the advantage of the substantial derivative, it does lot of help for us. Just because it expressed a Lagrangian rate of change in terms of Eulerian field, the number of steps required were very less. Look at the Lagrangian approach, we had to find out position, velocity, acceleration, substitution in terms of time, etc. But remember this is more natural. Why? That we did right from your particle mechanics principles. This is more closer to measurement, because velocity field is what you are measuring, okay, and that is the significance of substantial derivative. Okay. It gives you a meaning of Lagrangian derivative just from Eulerian measurements. Okay.